Welcome back to our series on statistical methods. I'm Mark Ledbetter, and this is lecture 23, and we are entering into chapter 5, and we're going to discuss a factorial ANOVA or factorial design or factorial model, all different ways of saying the same thing. So let's get started. Welcome. In this video, we're going to go over a factorial ANOVA. This is for chapter 5 in the book. So what are factorial designs? Well, it's where we study two or more factors, and we also investigate the interaction between factors. The most efficient, factorial designs are the most efficient for this type of experiment. In each trial or replicate of the experiment, we test all possible combinations of the levels of the factors. So let's define a main effect. Since we have more than one factor now, we define the main effect is the change in the response produced by a change in the factor level. So we're going to say that factor A, we're going to start with a two-factor ANOVA here, that's factorial, and we're going to say that factor A has A levels and factor B has B levels, and we're going to replicate all A-B treatment combinations, and we're going to do that n times. So replicates n. For each of these combinations, we're going to repeat the measurements n times. Okay, so it's said that factors in a factorial design are crossed. And when we look at, if you think about matrix and or cross products, that is the reason. So our example of a model here is a two-factor experiment where factor A has two levels, let's say high and low. We'll say high is a plus and low is a minus, and the same thing for factor B, two levels, high and low. So now we're going to draw a picture, and you'll see that we have factor B in the Y and factor A in the X, and we've got the low and high level of B, low and high level of A, and we've given the response, it's in the corners as it says here, so this would be a 30 when we're at a factor A is low and factor B is high, 20 when factor A is low and factor B is low. And then we have 52 when factor A is high and B is high, and 40 when factor A is high and factor B is low. So for a two-factor experiment, we can easily calculate our main effects. So we're going to take the average, the main effect for A is going to be the average of the high of A minus the average of the low of A. So when A is high, that is the 40 and the 52. And when A is low, it's the 30 and the 20. So we average up 40 and 52 and subtract the 30 and 40 averaged. That gives us 46 minus 25, or 21, as our main effect for factor A. So it's 21 units, whatever units we have here. Okay. Now, that's looking at it from factor A. Let's look at it from factor B. So we're going to look at factor B high is going to be up here, and factor B low is here. So we average 30 and 52 and subtract the average of 40 and 20, and we get 11. So we've done that here in this line. All right. So for a change in A from low to high, the average response increases. As we go from low to high in A, the average response increases 21 units. Remember that we're talking about means or averages. For a change in B, when we go from low to high, the average response increases again by 11 units. That's because these numbers are positive. If they were negative, then it would be decrease. Okay. So we've got this block, but let's look at, first we're going to note that the procedure for 3 levels is different than this, so don't try to use the same method for 3 levels. Hopefully we'll have time to discuss 3-level factorial. Okay, now interaction. Interaction is something new. We haven't really discussed interaction before, so we want to see what interaction looks like. Okay, so what we're going to do is we're going to look at a different, this is model 2, if you will, and up here this was model 1. Now, so the interaction says the difference in response is not the same at all levels of whichever factor we want to hold constant. So if we look at factor A, let's look at the low, and we go from 20 to 40. And when we look at high, now we go from 50 to 12, so it's reversed. Likewise, if we look at factor B, the low level, then we go from 20 to 50. The high level goes down from 40 to 12. So they're going in different directions here. All right. They don't have to be going in different directions to have interaction. They just have to go at different rates to have interaction. Okay. So for factor B, the low level is 50 minus 20. So factor B, the low level, we have a difference of 30 between the 2 levels. And for the high level of factor B, we have a difference of 12 to 40. So that's 28, negative 28. So we can get the same thing here by taking the high level minus the low level, so the average. So we could take 12 plus, let's see, would that be right? We could take 12 minus 40, the difference. So we're going to take 12 minus 40 and then average that, and then 50 minus 20 and average that. And so we have the high minus the low, and we're averaging it. There's 2 of them. We get a negative 29, and that's big, okay? So let's take a look at an interaction plot, okay? So we have 2 plots here. The first is for model 1, and we have no interaction. So what we've done here is we put factor A on the x-axis and factor B, or the response on the y. And then for each level of B, we have a different plot. So for B at the high level, or B plus, and then B at the low level. So if we take B from the first, and we're going from 30 to 52 over A, so B at the high level, we're going from 30 to 52 as we go from low to high across A. Okay. And then for B minus, for the low level of B, as we go across A, we're going from 20 to 40. And that's what we have drawn here. All right. Now for model 2, where there is interaction, we do the same. We have factor A down here and the response in the y. And we draw a line for B minus. You'll see B minus goes from here to here. And we go from 20 to 50. So 20 to 50 for B minus. And for B plus, we go from 40 to 12. So we go from 40 to 12. And you see that the lines cross. If they cross or touch, there's definitely interaction, but they don't have to be. They just don't have to be. They don't have to cross. They just have to have different slopes. All right. But it says that while graphs are a good way to communicate significant interactions, they should not be used as a sole technique because they can be misleading at times. All right. So here we say in model 1 that B minus and B plus profile lines are approximately parallel, and that indicates no interaction. In the second model, we say that the B minus and B plus lines are definitely not parallel, and that indicates that we do have interaction. Okay. So there is another way to illustrate interaction, and that's through regression. Suppose that both factors are quantitative, and we could use a regression model. And so we'd use this model for regression. We'd say y is equal to beta naught, which is our intercept, and then beta 1 would be the slope for x1, factor A, and beta 2, whoops, typo, x would be the slope for factor 2, or x2, and then we'd have beta 1, 2 would be the slope for the interaction between x1 and x2. And you'll notice that the way that we do interaction is by multiplication, and then we would have epsilon for our error, okay? And x1 is going to be coded on a scale from -1 to +1, so would b, and x1 times x2 would be the interaction of A and B. The parameter estimates are related to the effect estimates. For our first model, the effect of A was 21 and B was 11, both positive. And what we can do for this model, and it's kind of special, is we can take because of the way we've coded this, we can take the 21 and divide by 2 to get our beta 1 hat, which is 10.5. And for beta 2 hat, we take 11 divided by 2 and get 5.5 as our estimate. And then for our interaction effect, we would take 52 minus 40 divided by 2 minus 30 minus 20 divided by 2, and we get 1, okay? So, so that was our effect for AB in the first model. We didn't calculate that before. So it's only a 1. And then we calculate beta hat 1, 2, the interaction. We take a half of that interaction effect, and we get 0.5. And then beta naught is an average of the 4 treatment effects. And again, there's some mathematics going on behind here, which we're just not going to get into right now. So we take and average those, and we get 35.5. So our model would look something like this. Y hat's equal to 35.5 plus, that's our beta naught, or our intercept, and then plus 10.5 times x1 plus 5.5 x2 plus 0.5 x1 x2. And these are least squares estimates. Okay. And it says since beta hat 1, 2 is 0.5, which is very small relative to beta hat 1 and beta hat 2, the interaction effect is relatively small and could be ignored. But again, I would tell you to check that statistically before you drop a parameter out of a model. Okay. And if we did drop it, then they're saying that we're just ignoring it. We drop it out of the model, and we get this estimate for the line. In real life, you would run the fitting again with regression, and you get slightly different numbers for your parameters here. Okay. So I did my best to draw this response surface plot for the first model. This is for model 1, okay, where we don't think we have any interaction. And this, we've got y in the y-axis, and we've got x1 in this direction, and I've written it wrong. It's x2, not x squared. Let me see. So this was x2 in that direction, and we went from -1 to +1 in x1, and we went from up to 1 again on x2. Yeah, -1 to +1 on x2 as well. And so looking at our values, we've plotted this response surface in here, and it's basically a plane, a flat plane. And because it's a flat plane, if we took a contour of that, a contour plot, x1 here and x2 here, then we'd have straight lines for our contour plot. And they're parallel lines, okay? For the second model, I couldn't quite draw the response surface plot well. Take a look at the book. It's a curved surface, so even more difficult to draw. And their contour plot, again, x1, x2, now instead of having straight lines, you've got curves. And so that's because the response surface is a curved or twisted kind of plane. Okay? In the second model, we calculate the effects. We didn't calculate the effects of A or B before. We calculated the interaction effects, which was negative 29, fairly large. For effect A, we go through the high, average of the high minus the average of the low, and we get a 1, which is pretty small. And then for effect B, we do the same, and we get a negative 9. You'll notice that negative 29 is large in comparison to these two values. And so that tells us that the interaction is significant here. Okay? So let's talk about some advantages and disadvantages of the factorial design. The advantages, it's more efficient than a one factor at a time experiment. It's also more efficient than some of the special designs that are out there, such as Latin squares and what have you. It allows us to determine if there's interaction or not, or to test for interaction. And it allows the effects of a factor to be estimated at several levels of the other factors. The conclusions are valid over a range of experimental conditions. The disadvantage is that it could be expensive. There's many factors. For our design, we had 2 factors and 2 levels for 4 experiments. But as soon as I go and add another factor, it's 2 times 2 times 2, that's 8. And for 4 factors, 2 times 2 times 2 times 2 is 16. Then if we talk about a 3 by 2, so we'd have 2 factors of 3 levels each, that's 9 experiments. And then 3 times 3 times 3, if we had 3 factors at 3 levels, that's 27. And 4 factors at 3 levels, that's 81. So the number of tests increase exponentially. So it can be expensive. And that's why people have come up with some special designs that are not as efficient or effective, but they may be good enough for certain situations. Okay. All right. So that's the disadvantages, that you can end up with a lot of different tests and replications, which can cost you time and money. Okay, let's take a look at our model. And we have our model here. Yijk is equal to mu plus tau I, which are our effects, treatment effects for factor A. Beta j's, which are our treatment effects for factor B. And then we have our tau beta ij's, which are our interaction effects for the ith and jth combination. And then we have our random error epsilon ijk. I goes from 1 to A, J goes from 1 to B, K goes from 1 to N. We're only going to talk about fixed effects. And so if both factors A and B are fixed, then we have our usual constraint that the sum of the tau i's are 0. The sum of the beta j's are 0. Now we have to also look at our sum of our interaction effects, and notice that I'm only summing across J here, but the sum across J is equal to 0. Or if I only sum across I, it's still 0. So of course if I summed across I and J, I would also get 0. Okay. In for the balanced design is A times B times N. So the number of levels of factor A, the number of levels of factor B, and the number of times we replicate each factor combination. We have three hypotheses that we can test here. Since they're all fixed effects, they're all about the effects being equal to 0. So the taus being equal to 0, the betas being equal to 0, and the tau betas being equal to 0. And of course the alternative is that at least one is not 0. All right. Let's talk about the calculations. For the sums, I have the sums on this side and I have the means over here. So we have the overall sum, which is the sum across I, J, K of the observations. So this is adding up all the observations in the experiment. To get the overall mean, I divide that by the total number of observations in the experiment. And for yi dot dot, I add up all of the observations for the ith treatment level of factor A. And so that means I'll add across B and N. And then to get that average for that ith level, I'll divide by Bn, B times N. But now we have y dot j dot, which is summing across the i's and the k's, but not the j's. So for the jth level of factor B, I'm adding up all the observations in that level. And then to get the average for that, y dot j dot bar, I divide by A times N, the number of observations in the jth level of factor B. And then we have the cell means. So for the ith level of factor A and the jth level of factor B, we sum across just the N. So how many we have in that one cell. So to give you a kind of a picture here, we sometimes will say, let's say low, high, and this will be A, and B would be low, high for a two-factor, two-level. So we call this a 2x2 factorial design. And then, so this is I equals 1, this is I equals 2, this would be J equals 1, J equals 2, and then I'd have y111, y112 to y11n. And here I would have y121, y122 to y12n. And then for the high level here, I'd have 21, y211, y212, y21n. And here we'd have y221, y222 down to y22n. All right? And so I hope that by writing this out a little bit, that this helps you visualize. So if I was looking at I1, J1, I'm looking at this cell, and I would add up those values to get this sum of yi j dot, and then there's n in that cell, so I would divide by n. For yi dot dot, I would add these two for I equals 1, okay? And so this is across j equals 1, j equals 2, and n equals 1 to n. So I would add up these 2 times n observations, because j is 2, and so I would have to divide by 2 times n, or b times n. And then for j, it would be in this direction, the same thing. All right, so I would add across I equals 1 and I equals 2, and k, it goes from 1 to n. So I'd have a times n observations. That's what I would divide by. So I hope that helps you visualize this and understand the equations a little bit better. So let's look at our ANOVA table. Again, just like in every other model, we can break down the total sums of squares here, and we can break it down into different components. We can break it down for factor A, for factor B, the interaction, and the remainder, which is the error. Okay? And A, the degrees of freedom, would be A minus 1, of course B minus 1. For the interaction, we show multiplication, and so that is what you do, A minus 1 times B minus 1. And then if you subtract these three quantities from the overall ABN minus 1, you'll find the error, which is AB times N minus 1. All right. Now, as per the same pattern that we've seen, for the treatment sums of squares for A, it's going to be yi dot dot bar minus the overall quantity squared. And we're summing across all three indices, but there's only an I here. There's no J or K, so those just end up being repeats, and so we have a multiplication of B times N. Same thing for B, A times N, and then it's Y dot J dot bar minus Y dot 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 bar, and then that quantity squared. For AB, we don't have any N's, so we can bring N times this quantity, and here we're going to take Yij dot bar, because that's for the AB combination. We're going to subtract off the overall, or the ith, whatever I this is, we're going to subtract that mean for the ith level, and we're going to subtract the mean for the jth level, and then we end up adding back one of these y overall means, y dot 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 bar. Okay, and again squaring, and then our error is just yijk minus the means for each of the cells, that quantity squared. All right. We calculate the mean square the same way as we have. We take the sum of squares divided by the degrees of freedom for each of these. And the mean square, so the F statistic, we're going to divide MSA divided by MSE because it's fixed. And again, because it's fixed, we're taking MSB divided by MSE and MSAB divided by MSE. Remember, if A is fixed and B is fixed, then AB has to be fixed. And these are, here are the distributions. We take the F distribution with alpha, and we have the degrees of freedom in the numerator, degrees of freedom in the denominator, which is always the degrees of freedom of error. All right, so now we can test for, once we've made the test, we can, if there is a significant effect somewhere, whether it be A or factor B, then we can test for those main effects. If there's interaction, then we will want to be careful, okay? So when there's interaction present, then we don't look at just A by itself or B by itself. In fact, I want to point out that A could be insignificant, B could be insignificant, but you could still have an interaction effect. Okay. So A doesn't have to be significant, or B have to be significant for there to be a significance between A and B. All right. Now, if there's an interaction, here's another thing. It's a practical thing. So if the interaction is present, you never remove the underlying factors for that interaction. So in this case, we only have two factors, okay? But what if I had A, B, and C, okay? So if I had three factors, I'd have A, I'd have B, I'd have AB, miss C. Don't forget C. And then I would have AB, AC, BC for the pairwise interaction, and then I'd have ABC. So let's say that none of the main factors were significant by themselves. But if AB is significant, that interaction is significant, then I would keep A and I would keep B in the model. Okay? Likewise, if AC was significant, I'd keep A and C in the model, but not B. And again, saying that all the main effects were not significant. And so forth. Of course, you might now conclude that if none of the main effects were significant, and none of the, even none of the pairwise interactions were significant, but if A, B, and C were significant, then you keep everything in the model. So everything that has an A has to stay. Everything that has a B would have to stay. And everything that has a C would have to stay. So the rule is that if you have some type of interaction that's significant, then you keep everything that has any one of those letters in it. Okay? So let's say, for instance, that we had, we'll keep the same model, but I'll clean it up a little bit. We have A, B, C, A, B, A, C, B, C, and A, B, C. So let's say that, so to be clear, if B, C were significant, then I keep all factors that are not as complex as this, but have any one of those letters. So I don't have to keep these because they're at the same level as BC, all right? And they're tested individually. If they're not significant, we don't worry about them. But I would still keep B and C regardless of whether they were significant or not. And then if A, B, and C is significant, then I will look at all two-way and all one-way effects, single effects, and anything that have these letters in them would remain. So to give you a little better idea of what I'm talking about, let's expand this to 4. So I've got A, B, C, D, A, B, A, C, A, D, B, C, B, D, C, D. I've got A, B, C, A, B, D, B, C, D. And then A, B, C, D. All right. So, if nothing was significant except this one, B, C, D, then I would keep C and D. I would keep B and C, okay, and I would keep B, C, D, because those are all contained. BC is contained in this, CD is contained in this, and then of course B, C, and D are contained in this. So those are the ones that I would keep. So sometimes it takes a little more complex model for you to see the pattern here. All right. Now, when interaction is present, then we fix, let's say, factor B at a specific level and applies Tukey's test to the means of factor A at that level of B. So when we go to our example in the next video, then we'll see what we're talking about there, okay? And we'll do our normal adequacy checking, model adequacy checking. We'll analyze our QQ plots and for the residuals, and we'll analyze our regular residual plots for any variance issues. And I want to note that if only one observation per cell, if we only have one observation per cell, in other words, n is equal to 1, we cannot test for interaction. So there's no way to tell if interaction's in the model or not. So just be aware of that. You can test for the main effects, but you can't test for interaction if you only have one observation per cell. Well, that's the end of this video. I hope it has helped you understand factorial designs. All right, that's it for this video. If you have questions, please make sure you come to virtual office hours. If you need help prior to office hours, by all means email me. But when you email me, if it's about a problem, then email me what the problem is, because I may not have it available, and then your work on that problem so far. If it's code, then by all means send me a copy of the code, and in the email tell me where you're having the problem and that you need help. And I will get back to you as soon as it's possible. Please take care of yourself and stay safe, because we want to see you here next time.